All right, hello, this is Nathan Hall, and I'm going to be discussing my code for the lane detection homework assignment for ENME435. So to start, I'm going to be running through the functions that my code uses. This function right here grabs each frame from the video. This code right here snips the bottom half of the image so I can focus closer on the road and lane lines. And then this further narrows down the lane lines and road directly in front of the car to help focus on that area again. Then the threshold function. So one thing I changed from the class code is I was having a much easier time using the grayscale to detect the lane lines than the HSV color space. So I used this. And another thing that I did was I adjust the threshold for this grayscale based off the average brightness of the image, and this helps me transfer my code across each image with without having to make any changes to my code. Then there's the blur image that helps gets rid of any noise. And then the edge detection image, which recognizes a sudden change in color in a sense to figure out where the gray road ends and then the white lane starts, and it picks up on the outline of each lane. Finally, there's the image lines function that detects lines of the edges based off of a certain amount of votes, then returns a rho and theta value for said line. Then the plot lines function. So to start, I only want this code to run if rho and theta are not equal to 0. And additionally, if rho is greater than 0, through tinkering with the code and being able to see it, I was able to realize that, okay, this is a left lane, and then draw it accordingly. And then if rho is less than 0, I could then determine that it was a right lane line and then draw that accordingly. And that's also where I differentiate a green line right here and a red line right here. And one thing that I changed from the class code is the coefficients attached to these A and B values. And for each of these, this helped me make sure that the line didn't go to the end of the frame and only was like a little bit in front of the car detecting the lanes. Because when it went all the way and there was crossing, it was just kind of, that would probably get in the way of the function of the car if the lines were going all the way to the end of the image. Then another thing that I adjusted for first, also I have else functions that return the image just because if these conditions aren't true, I still want to return the image even if the lane lines aren't on the image or the frame. And another adjustment, a new function that I created is a mirror function. And basically what you'll see further in my code, this is for if lane lines are not able to be detected. It basically flips either the right lane to the left lane or the left lane to the right lane. So say, for example, this was a right lane and I wanted to mirror it to the left. So first I draw the right line how I would normally. And then I create the same, I set for the left lane line, I set the Y values equal because for the most part, they're going to be flipped over a vertical axis. There might be a little bit of a curve, and that might be a little bit different, but for the most part, it's going to be flipped vertically. And then I have a threshold. I have a bunch of if and else ifs and else statements here that determine based off of where the Y value is for the right lane line, how far I want to reflect it over the vertical axis for the left lane line. So if the Y value's, further away, then I don't have to reflect it as far because it's like this. So the further it is away, then the lines will be closer and I won't need to flip. I'll need to flip the lane line a lesser difference. But if then the Y value is large, then the field if the end of the line is like very close, then you have to you have to flip it further than you would if you were all the way over here. So the field of view is in a sense larger at that particular distance, and the range to flip is much greater. So that's what all of these if and else if statements are for. And then again, I return the image even if these conditions aren't true. And then here I just do the same thing, but flipping the left lane to the right and adding instead of subtracting the x values. So here starts my main function. So first I load the video and then I initialize a counter variable that helps keep track of the frame number while looping through the video. I also create two lists with row values of filled with none, which will then, and then previous left row values with previous right row values. And these are just initialized so I can use them further in the code. For example, I have to initialize these row values because there may not be row values created further in the code, but I need them to be, even if row values and theta values aren't created, because the if statement for say isn't true, I still need these to be passed into the depending later functions. And then I create a while true, so I want to keep running through this loop as long as the video until the video stops playing. And I also initialize some videos here for further use of my code. And these alert left and alert right are to detect blind spots. And the shadow function, which you'll see, is also used to be able to detect whether it's bright enough outside for there to be a shadow. And then here I grab I grab each frame of the video so then I can obviously make adjustments to that specific frame, and it keeps going through each frame. So if there is a frame available, then I'm going to start this if loop. This right here, I created a left blind spot that kind of gets the left front view of it, which you'll see later in the code helps me detect if the lane can't be detected there because of a shadow or something. And then I also create an HSV of this left blind spot and record the average brightness value. So the hue saturation value, I record the value number and find the average to detect if there's a blind spot or like shadow per se blocking the lane. And I do the same thing with the right lane. And then finally here, this is a HSV. I take an HSV of the entire frame and I take the average brightness of that frame. And by using this right here to, again, get the average value or brightness. And then I say, if the brightness is this high, then there's potential for a shadow to be, because if it's like morning and the sun's not quite out yet, there's not going to be a shadow, so it's not something you have to worry about. I only want because then the darkness in the left blind spot per se up here will, I only want it to think that it is a shadow if there is a chance to be a shadow, because if it's that early in the morning and it's not very bright outside, well then yeah, this left brightness might be low enough even if there isn't a shadow. So I essentially only want to, have this take account if the brightness is high enough for that to be the case. And then I have a counter greater than 20, just because at the beginning of the first video, there's a sudden like brightness at first. So I just want to account for that. And then here I go through the standard functions of snipping the frame. I mask then the snip, and then I threshold that with the grayscale. I blur it, and then I create the edges and my lines. And then here I initialize empty lifts for the left row, left theta, and right theta for the left and right lane lines. And then if there is lines to detect, I enter this for loop right here, and it basically records whether it fills values in for the left rows and left thetas. So it creates a list for that frame of all the lines, and it adds together the left row. It puts all the left rows in all the row values that align with the left lane into a list, and then the same thing for theta, and then all the row or theta values that align with the right line into a list. And then right here, I take the mean of this left row list and right row list, and also I take the mean of the left theta and right theta, so I get a final row and theta value, so I can draw a single line with my plot hue lines function. And these if values right here are to still ensure that even if both of these conditions aren't true, if there isn't a left row to record, but there is a right row, I still want to pull out that right row value, because obviously if I need to mirror the right row to the left side, well, then I need to, if I need to, yeah, if I need to mirror the right row to the left side, well, I'm still going to need to record a right row value, which wouldn't be the case here because both of these conditions need to be true. So even if this isn't true right here, then this is true, and I can still pull my right row value. And that's what it does again here for the left row value, and then the right theta and left theta. And then here I record the previous left row values and previous right row values and keep track of them, continuously storing them in a list. And then here's where my shadow variable comes into account. I only run this code if there is a potential for a shadow. So if it's bright enough outside, and essentially if the left brightness in my left blind spot is less than this certain value, and the right row value has not changed, this one right here, because the row value is like in a array right here, so it's pulling the right row value, then if the right row value doesn't have a sudden change, then I want to perform the mirror function of the right lane and also create an alert left variable, which I'll talk about later in this code. But essentially, because if the left brightness all of a sudden becomes less than 70, but then the right lane changes, or like the right row value changes like very suddenly as well, well, then that's probably the right lane probably changed too, or that left brightness decreasing probably isn't just due to a shadow or a sudden object blocking the left lane, and they're like maybe the lanes aren't there anymore. So I also want to make sure that the right row value, which then aligns with the right lane, does not change suddenly. I want to make sure that's staying consistent, so okay, well, we still are on the road and there still should be a left lane that's being detected. And then I do the same exact thing with the if I wanted to mirror the left to the left lane to the right lane, I do the same thing here. And here's where I'm actually going to, so if my row values from my left and theta values are true, then I want to just plot the left lane normally to the screen. And the reason I have the alert left values here is, one thing I noticed is that when these left brightness becomes less than 70, so eventually sometimes it can't print these row values and theta values. Sorry, okay, I just wanted to make sure I was still following. So sometimes it can't print the row values and theta values, but sometimes it still can. Like one thing I was noticing is when it came up on this, then the second video, there's a car that creates a shadow, and when it comes up on it, the line on the left just kind of starts glitching out because it's not able to basically pick up on the because of the left brightness is down. So that's why if the left brightness is less than 70, then I create an alert left variable that basically says, all right, well, I don't want to plot this left lane that is like glitched out, so I'm not going to show that left lane line. And you'll see where it still kind of sometimes flicks to the left lane kind of glitches out. But this is kind of to mitigate that, in the sense that, all right, well, yeah, if the shadow's there and you're still getting, eventually you won't get left and row values because it won't pick up on anything at all, but eventually it will pick up on, at first it still is able to, but they aren't accurate. So I basically would say, well, they aren't accurate, so don't plot them. And said, I still want to print the snip to the screen though. And then I do the same task with these values here. And basically, yeah, I do the same exact thing with the left lane, with the right lanes. This should say right. Yeah, so I do the same exact thing with the right lanes as I do with the left. So first, I'm gonna run through the first video and see how my code does with that. So here's the first video. And here's my blind spots that I created. So as you can see, it is picking up on these lanes pretty well. And this is pretty simple as it, there's not much getting in the way, and the brightness is at a pretty good state for detecting lanes. And what you'll see is when you come up on this bright spot here, it's able to recognize that and then adjust the threshold accordingly. Because that was one of the issues that I run into this code originally with, is that bright spot just caused a error in the thresholding. And one thing that does throw off this is the bridge, because the left lanes on that seem to all of a sudden go to the left, and so that bridge throws it off suddenly, which is definitely still a flaw in this code. All right, and now I'm gonna run through the second video. So again, here are my blind spots. So it's running through pretty well. And as you see, as the person switches lanes eventually. So switching lanes, obviously the lines are inaccurate for a second, but then they disappear and then they readjust to the new lanes. And here you can see the left blind spot. This shadow of the car does not seem to throw off the code at all. So the line still prints pretty well. But then as you see, as you come up on this car, the shadow of it is going to basically get in the way. And so the left lane is eventually going to be based off of the mirroring of the right. And as this goes further out, there's less you have to mirror over. And as you're closer, then you need to mirror it a greater distance. But as it's all the way over here, you need to mirror a lesser difference. So it's kind of running through these thresholds to kind of stay as close as possible to being accurate over the line. And there is still some noise in the code. So it's definitely not flawless, but in general, it's able to keep the general direction of that left lane. And there's some other noise that comes up right here that throws it off for a quick second, but it fixes itself. So overall, I think it applies to both video. As you can see, I didn't change anything. It was able to change the threshold based off of the average brightness, and it was able to detect the shadow because it was bright enough. There was a chance for a shadow, and then because there was a chance for a shadow, it recognizes, all right, well, there's a shadow in the left lane. Let me start mirroring the right lane. And one thing I did notice is that another flaw in the code is that when the car comes up on that exit and there's a lot of lines there, it kind of, messes with it a little bit, and that leads to a little bit of noise in the lanes. But overall, I think it did a good job. Some improvements I think could be made in terms of hardware. So instead of having to take the average brightness of the entire image, I think that a photoresistor maybe aimed up at the sky to get the brightness would be more, because obviously there's a lot that could affect the brightness of the frame as a whole. And so I think having a photoresistor that maybe aims to the sky and gets a more accurate reading and then is able to change the threshold. I only have, one brightness that kind of adjusts between these two frames, but I think a photoresistor that's aimed to the sky, that like maybe an algorithm relates that to the threshold so that the threshold continuously changes for any brightness. I think that would make it much more accurate. I think maybe a LiDAR sensor that detects if objects are close to blocking the lane or blocking the lane. Like if something blocks the lane for a second, it would be able to detect that and maybe make sure that the left lane doesn't it keeps the left lane going, or like alerts the person that there is something moving into the left lane. So while it still is able to detect the lane, it also is able to detect an object moving closer to it. So those are the two things I think would be best for hardware. And software, I think an automatic algorithm for mirroring the lines would be beneficial. Again, I have a lot of if and else if statements, but I think if you found an algorithm that bases the distance of y, how far out it is and then adjust the x distances accordingly, so you get a very accurate mirroring of the right lane to the left lane, I think that would be beneficial. And then I also think that keeping track of sudden and to keeping track of sudden changes in the rho and theta values would be beneficial in terms of eliminating noise, because I know there was a certain parts of my code where it comes across something and all of a sudden the lines just kind of like glitch out. Like maybe getting rid of that noise by, averaging the certain amount of previous left, averaging the, I don't know, previous 10 rho and theta values, so that if it changes over a sudden frame, like obviously you almost need to change over multiple frames for it to be definitely something that happened instead of just some noise. So I think that would also be beneficial. And another thing that I noted, instead of detecting just one straight line, like when it comes across that exit, I think it would be beneficial if it detected all the lines there, because there's two lines that converge as the exit converges into the road. So, and there was also some dashed line, like lines horizontally on the exit. So I think it was, if it was able to making this code being able to detect all those lines and then creating statements that tell it to react accordingly, so it doesn't pick up on that exit line and is able to be like, all right, well, these are all lines, but this is the line that I want to notice. I think that would also be beneficial. And then I think another thing that should be noted is, um, when I was running through this code, you can't tell, there's no difference really in a dash line and a straight line. So I think adjusting the lines function to be able to defer from solid and dash lines by figuring out maybe the length of the line. This only returns rho and theta, but if it was maybe able to determine the length of the edge, finding a way in this code to detect that, and then being able to differentiate between a dash line and then a straight line would be beneficial. As that's a big difference. You can merge over a dash line, you can't over a solid line. So I think these are all things software wise that would be beneficial, and paired with the hardware of a photoresistor and obviously a lidar sensor, which we've talked about in class, about a lidar sensor being paired with cameras, because I think a lidar sensor, with if a car is coming up on the left right there, instead of having to create like a left blind spot shadow, if that lidar sensor is able to see that car there, then it might know that those lanes aren't going to be visible. So I think these are all things that could be added. So yeah, that's my code, and overall I think it did a good job. There are still flaws in it, which I think these hardware and software improvements would address. Thank you.